In this video, you'll encounter a new type of substitution reaction, electrophilic aromatic substitution, with its own unique mechanism, after which we'll look at electrophilic aromatic halogenation, nitration, and sulfonation, and the Friedel-Crafts reactions alkylation and acylation. Much like the pi electrons in the carbon-carbon double bond of alkenes, the pi electrons in benzene can be used to react with electrophiles. In alkenes, the reaction that usually occurs is electrophilic addition. In benzene, that does not occur. If it did, you would start with an aromatic starting material and you would end up with a non-aromatic product. In order to retain the aromaticity of the ring, benzene and its derivatives usually undergo a substitution reaction where a hydrogen on the ring is substituted for an atom or atoms that come from a suitable electrophile. Therefore, benzene and aromatic compounds will undergo substitution reactions instead of addition reactions. This is a new type of a substitution reaction called electrophilic aromatic substitution, and it has a mechanism that is very different from the substitution reactions that you've seen already, SN1 and SN2. The overall transformation in all electrophilic aromatic substitution reactions is the substitution of a hydrogen on the benzene ring for the atom or atoms that come from the electrophile. Regardless of whatever specific electrophilic aromatic substitution you're considering, be it halogenation or nitration or sulfonation or the Friedel-Crafts reactions, they all follow the same general two-step mechanism, which is shown here. The first step is the slow step. That's where benzene is acting as a nucleophile, using a pair of its electrons in the pi system to make a new bond between one of the carbons on the ring with the electrophile. So this bond between C and E, the two electrons here, came from this double bond right here. You end up with a resonance stabilized cation. The resonance structures are shown below here in this reaction energy profile. As you know, carbocations have three possible fates. They can be trapped by nucleophiles. That's not going to happen here because that would end up being a addition reaction overall, and you'd lose the aromaticity in the ring. They rearrange to carbocations of equal or greater stability, or they can lose an atom on the carbon next door to the carbocation, and then the two electrons in that bond could go to reform the ring. That's what happens here because the ring wants to become aromatic again. So a Lewis base removes this proton, these two electrons go back into the ring, and you end up with an aromatic product, and you can see that overall you've substituted the hydrogen on the ring for the atom or atoms from an electrophile. So once again, all electrophilic aromatic substitution reactions follow this same general two-step mechanism. What's different, however, is the electrophile and also how you make that electrophile, how you form that electrophile, which we'll look at now for halogenation, nitration, sulfonation, and also the Friedel-Crafts reactions, which are carbon-carbon bond-forming reactions. As stated, each of these electrophilic aromatic substitution reactions follow the same general two-step mechanism that was outlined on the previous slide. What's different is the nature of the electrophiles and how you generate them. For halogenation, the electrophile is molecular halogen, bromine or chlorine. Alkenes react very readily with molecular halogens, bromine or chlorine. Benzene, as you know, is less reactive than typical alkenes. So we have to make the molecular halogen more electrophilic. We have to juice up the electrophilicity, make it a better source of X+. And the way that that's done is by using a Lewis acid, and typically it's iron 3 halide. what happens is one of the halogens forms a bond with iron. So iron is acting as a Lewis acid, accepting a lone pair of electrons from one of the halogens, and you end up with a species that looks something like this or this. So the actual species that reacts with benzene could either be drawn like this, or you could consider it to be something that looks like this. And either way, this is a source of X+. So this is the electrophile, either this or this. Doesn't matter which one you draw. For nitration, the reaction involves concentrated sulfuric acid and concentrated nitric acid. And you'll have a lot of species being formed, protonated species. If I take nitric acid and I protonate it with sulfuric acid and I lose a molecule of water, I'll end up with a nitronium ion. Here we have nitrogen with a positive charge. This is a very strong electrophile, and this would then react with an aromatic ring via the typical electrophilic aromatic substitution mechanism that was shown on the previous slide. For sulfonation, something called fuming sulfuric acid is used. That is sulfuric acid that has SO3 dissolved in it. SO3 is a gas, and so therefore the material actually has fumes of SO3 coming off of its surface. SO3 has an oxygen with non-bonded electrons, and so the species that reacts with the benzene ring via electrophilic aromatic substitution to replace the hydrogen with a sulfonic acid group is protonated SO3. All right, for this one, let's actually write out the electrophilic aromatic substitution mechanism so I can demonstrate to you that it's basically the same mechanism that you saw on the previous slide. In the presence of benzene, the protonated SO3 would form a bond with one of the carbons on benzene. So benzene is the nucleophile, this is the electrophile. I'm going to make a bond between this carbon and this sulfur with these two electrons, these pi electrons. I will break the bond between sulfur and oxygen, and I'll end up with this resonance stabilized carbocation. I've not drawn the other resonance structures, but if you want to see them, you can take a look at the previous slide. That's the first step in the mechanism, the slow step, where benzene is a nucleophile reacting with the electrophile. The next thing that happens is we lose a proton on the carbon next to the carbocation, and the two electrons in the CH bond go back into the ring, and we end up with a benzene ring once again. It's possible by electrophilic aromatic substitution to substitute a hydrogen on the benzene ring for either an alkyl group or an acyl group. So this is called an acyl group, C double bond O R. And this is done by two named reactions, the Friedel-Crafts alkylation and the Friedel-Crafts acylation. And in each case, the electrophile is going to be a positively charged species. So for Friedel-Crafts alkylation, the electrophile is going to be a carbocation. For Friedel-Crafts acylation, the electrophile is going to be an acylium ion. This is the best of the two Lewis structures of an acylium ion, but I showed you this one to indicate that this carbon is electron poor, is electrophilic, and could react with the electrons from the benzene ring. Please also note that in the Friedel-Crafts acylation, you're using something called an acid halide or acyl halide as a reactant. You cannot have on the R group hydrogen or OH or OR. The R has to either be alkyl or aryl only. Let's look at the mechanisms for the Friedel-Crafts alkylation and Friedel-Crafts acylation. Please remember that these are electrophilic aromatic substitution reactions. So we know that they're going to follow the same general two-step mechanism for all electrophilic aromatic substitutions. But what's going to be a little bit different here is how do you actually generate the electrophile? How do you generate the carbocation? In this case, they generate the carbocation from an alkyl halide. And in order to make this carbocation form in higher concentration and very quickly, they use a Lewis acid. Aluminum trichloride is the Lewis acid. So remember, just like boron, this has an empty p orbital, and it could form a bond with the chlorine of the acid halide. And you end up with a species that looks like something like this, with a positive charge on the chlorine and a negative charge on the aluminum. Don't be upset when you see the positive charge on chlorine. You might think, oh, how can I have a positive charge on a halogen? But if you think back on the chemistry of alkenes, you've done that before. You've formed those halonium ions. Remember, you're not isolating this. This is a mechanistic intermediate that only forms as a transient species. It doesn't hang around very long. As a matter of fact, as soon as you make this aluminum-chlorine bond, you've further weakened this carbon-chlorine bond. We already know that it's polarized toward chlorine, but once you put a positive charge on chlorine, it doesn't want to have that positive charge, so it tugs at the electrons in the chlorine-carbon bond. This carbon happens to be a tertiary carbon, so it lets go of the electrons, and you end up with a tertiary carbocation. This is the electrophile that gets involved in the electrophilic aromatic substitution mechanism. So this is done in the presence of a benzene ring. As soon as you form this carbocation, the typical two-step electrophilic aromatic substitution mechanism takes place. That is, benzene acts as a nucleophile. It makes a bond between one of the carbons in the ring and the carbon of the carbocation. So here it is here. We end up with a resonance stabilized carbocation. Didn't show all the resonance structures, just this one. And the second step, the fast step, is loss of a proton by some Lewis base coming by, taking the proton away, and the electrons in the CH bond go back into the ring, and you end up with the aromatic ring again. And you can see the catalyst is regenerated, you've lost HCl, and overall you've substituted this hydrogen for the T-butyl group, and the T-butyl group came from this carbocation. For Friedel-Crafts acylation, the mechanism is similar. We have the acid halide reacting with the aluminum trichloride catalyst. You make the aluminum chlorine bond, you break the carbon chlorine bond, and you end up with the acylium ion, very reactive electrophile. And the mechanism it'll follow the standard electrophilic aromatic substitution mechanism, and you will have overall substituted this hydrogen for the two carbons here from the acylium ion. So overall, an electrophilic aromatic substitution, electrophilic aromatic acylation. You've encountered carbocations before, and you're already familiar with the three possible fates of a carbocation. Carbocations can be trapped by nucleophiles, they can lose a proton on the carbon next door to form a carbon-carbon double bond, or they can rearrange to carbocations of equal or greater stability. So you always have to be on the lookout of potential rearrangements occurring in reaction mechanisms involving carbocations. Keeping that in mind, we can try to explain why is it that when you start with this alkyl halide, which has chlorine on a primary carbon, when you carry out the Friedel-Crafts alkylation reaction, you don't end up with this species, which you might think you get just by substituting this hydrogen for this group, attaching carbon number 1 to the benzene ring, but actually carbon number 2 gets attached to the benzene ring. You end up with a T-butyl group, just like before in the previous mechanism where we generated the tertiary butyl cation. The reason is you get rearrangement occurring. In the mechanism, it starts the same way. Aluminum trichloride will be used to remove the chlorine off of this carbon. Now, if I followed the same basic strategy I did before and I break this bond and I end up forming a carbocation, that carbocation is a primary carbocation. And you know that primary carbocations are very high energy. Do they exist? Yes, you can make them exist, but in all of the reactions that you'll be studying and that you did study last semester, under those conditions, the formation of primary carbocations can be avoided, and therefore you will not form any primary carbocations in any of the mechanisms that you encounter. So if you are doing a problem and you're writing a mechanism and you start to write a primary carbocation, you should stop and try to figure out another way to do the reaction that does not involve primary carbocations. So don't draw them. So what can happen? How can I avoid the formation of a primary carbocation if this chlorine wants to leave and I want to break this bond? Well, what happens is a rearrangement. The carbon next door to the carbon bearing the chlorine happens to be a tertiary carbon. So therefore, a hydride shift could occur. So this is the transition state here. It's not a mechanistic intermediate, but it's the transition state, the high point in the reaction energy profile. As I'm breaking this carbon-chlorine bond, I start to break the carbon-hydrogen bond, and I start to make this new carbon-hydrogen bond. So notice that this is a concerted process, much like you saw in SN2, where you had nucleophiles attacking a carbon at the same time that a leaving group leaves, and the carbon undergoing attack, nucleophilic attack, never gets a charge. The same sort of thing happens here. This hydride is shifting over and making a new bond at the same time that I'm breaking this bond. So this carbon is the one that's taking on some of the charge as I'm breaking this carbon-chlorine bond. As that hydride shifts occurs, what do you end up with? You end up with a tertiary carbocation. So that's why you end up with the tertiary butyl benzene as opposed to this isobutyl benzene, a substituent on the benzene ring. And the rest of the mechanism is exactly the same mechanism that you saw before, the standard electrophilic aromatic substitution two-step mechanism, benzene acting as a nucleophile. You make a new bond between the carbon bearing the blue hydrogen and the carbocation, and I end up with a resonance stabilized carbocation, loses a proton from the carbon next door, and you end up with overall substitution of the hydrogen for the carbons from the tertiary butyl carbocation. You should attempt these two mechanism problems. You have to propose the mechanism for these two Friedel-Crafts alkylation reactions, keeping in mind that carbocations can be formed from alkenes and they can also be formed from alcohols. On this page we have some specific limitations of the Friedel-Crafts reactions. These are important to keep in mind when you're trying to solve synthetic problems involving one step being a Friedel-Crafts acylation or alkylation. So as you plan your syntheses, keep these limitations in mind. First off, what we saw already, that you cannot form a new carbon-carbon bond in the Friedel-Crafts reaction where one of the carbons over here is a primary carbon. You get rearrangement. In Friedel-Crafts alkylations, we know that the electrophile is a carbocation, but these are high-energy carbocations, and these are strong carbon-halogen bonds, this vinyl halide and an aryl halide. You cannot form these under these reaction conditions, so therefore you cannot perform Friedel-Crafts reactions where the alkyl halide that you're trying to use is a vinyl halide or an aryl halide, because of the fact that these are very difficult to form. Another one, which is also very important and sometimes easy to forget is that for Friedel-Crafts reactions, right, not halogenation, not nitration, not sulfonation, but only the Friedel-Crafts reactions are very slow and not feasible when you have a strong electron withdrawing group attached to benzene. And we just defined in another video what a strong electron withdrawing group is. That is a polar conjugated functional group attached to the benzene ring, where these groups attached to the ring, this strong electron withdrawing group, can withdraw electron density from the benzene ring via a resonance effect. So for example, any carbonyl containing group or a nitro group or cyano or anything that's polar and conjugated to this benzene ring, that would make this ring a much poorer nucleophile. And it turns out that for Friedel-Crafts reactions, the reaction is hindered to such extent that it's not a feasible reaction to give you a good yield of product. So please remember, for Friedel-Crafts reactions only, not halogenation, nitration, or sulfonation, you can do those with strong electron withdrawing groups. But when the electrophile is a carbocation or acylium ion in the Friedel-Crafts reactions, you cannot do that with a strong electron withdrawing group attached to the ring. Another trap that sometimes people fall into is trying to put an aldehyde group or a formyl group onto a benzene ring by this type of a Friedel-Crafts acylation, where you're using this as a substrate. And I mentioned before that you can't have hydrogen here. This is not stable under the Friedel-Crafts reaction conditions. Equilibrium favors HCl and carbon monoxide. So therefore, that's not a feasible Friedel-Crafts reaction. In addition, the same thing here. You might be tempted, if you're trying to make benzoic acid, to do it by a Friedel-Crafts reaction with this species. Well, this species really is unstable. It doesn't exist. It falls apart, and equilibrium favors HCl and CO2. So these are not reasonable starting materials in the Friedel-Crafts acylations. There are other ways to do this, and we'll see it later on.